f of c, the function at some value c, is called the absolute maximum of f on the domain if that value of the function is bigger than or equal to every other value of the function. This just says, look, this has to be bigger than every other value on the function, all right, or equal to. And then the minimum is the opposite. It has to be smaller than or equal to every other value on the function. In either case, we call it global min, global max. These are also sometimes called the extreme values of the function. The extreme top, extreme bottom, right? Extreme values. And then local, it just says that, you know, to be a local max, you have to be bigger than all other points near C. So like locally. And that's very problematic. The idea of near is problematic, right? Isn't that problematic? It's subjective, right? Am I near you right now? Is this pretty close? You feel that? It's close. Too close? So, am I near SeaWorld? Compared to how close we are, am I near SeaWorld? Okay, how about the sun? Am I near the sun? No, SeaWorld seems very close compared to the sun, right? It's very subjective when it comes to what we mean by near something. So, if you're a math major, there is a more precise definition of this. And it's not, we have to deal with this. As math majors, near doesn't fly, okay? We have a more precise way of dealing with defining things, which I'm not going to get into here. For here, it's just visually, near is like that, right? Okay, we just kind of zoom in, all right? Okay, so we did all those, we did all those, we did all those. And now we get to our first theorem of this section, which is called the extreme value theorem. And this is a great theorem. We need it. Okay, if y'all understand what a theorem is, right? It's a statement that is true, that's been proven to be true. This class is not about proving the theorem. We are just using it. So the theorem says if you have a function that is continuous, what does it mean for a function to be continuous? What was our way of explaining continuous? You draw it without picking up your pencil. Okay, we talked about this way back in the day. Basically, draw it without picking up your pencil. Let's say that you have a function that's continuous on a closed interval. That means you're looking at something like this. Closed interval means B, we have 2 points. The function starts here and let's say ends here, right? It's defined everywhere in here. So I have to draw from here to here without picking up my pencil. So, I don't know, that would be okay? There's an infinite number of ways to get there, right? As long as it passes the vertical line test, which makes it a function, as long as it's continuous, and as long as we're on a closed interval, this theorem is true. So here's what it says. We've got this continuous function on a closed interval. Then we are guaranteed. So this is the statement. This is the condition. If this is all true, then here's what we can say. F must attain both an absolute maximum value and absolute minimum value. Has to. There's no way you could ever draw me anything that would go from this point to any other point without picking up your pencil where you didn't get to a max or absolute max and min. Do you believe that theorem? Can you think of a way that you could do it? Straight line. Oh, good. I'm glad you asked that. So what about this? And let me give you the value of it. I'm just going to make it up. Let's say it's 3. The absolute maximum value of this function is what? 3. The absolute minimum value of this function is 3. It attains both its max and absolute max and min. They happen to be the same thing. Remember, if you go back to the inequality, it said that the point had to be bigger than or equal to every other point around it, right? In this case, every point on here is equal to every other point. So it qualifies. Make sense? Can anyone think of anything else that you might be able to sneak past the theorem, maybe prove the theorem wrong and get your name written in a book somewhere? It's a theorem. It's been proven. Okay, there's no argument. You can't argue it against it. So I'm going to try and see if I can. Let's see if we can. Where is it? There we go. Oh, that's just me. Oh, this is just me giving you examples. So here's an example, right? There you go. So that I connected those 2 points with that straight line. I mean, not straight line, with that curve. It's nice and smooth. Didn't pick up my pencil. Does it have an absolute minimum? Yep. Where? Left end point, right? That's your absolute minimum. Absolute max is right there. It's kind of hard to see because of the way this is drawn, but it looks like it does like a little hump before it comes back down a little bit there. Can you tell? So this is our absolute max. That's our absolute min. Yes? Okay, I'm going to try a different one. Going to connect the same 2 points with a different curve. Right? Tried something different. Try to get fancy and come down here. No problem. Absolute min, absolute max, no way around it. Let's try something else. Straight line. The endpoints are your max, absolute max and min. How about that, though? What test? It's not continuous. So you tell me the theorem doesn't apply, right? So you can't use the theorem if the function doesn't satisfy the fact that it's continuous. So this is not continuous. You have a break. So good try, but no way. All right, so that's the theorem. Now, Fermat's theorem. Fermat's theorem says if f has a local maximum or minimum at some point. So if we have some local little bottom of the valley or top of a hill, if we have one of those and the derivative exists, that's the derivative, tangent line, right? If the tangent line exists there, then the derivative must be 0. The slope of the tangent line must be 0. All right, so let's see if we can understand this. I even put it here. This theorem is very important because it tells us that if we have a local max or a local min, that the derivative exists, then we must have a slope of the tangent line must be 0, so it must be horizontal. The theorem does not say that just because the derivative is 0 at a point, then we are sure that there is a max or min. I need to illustrate this a little better. Okay, so here's what the theorem is saying. Let's say you have a local max, and or let's say that you have a local minimum. All right? That point up here would be a local max. This would be a local min. The theorem says that so long as the derivative exists, that the derivative must be 0. So do you see that the slope of the tangent line there is 0? Okay? Everyone agree? The theorem does not say that if you look to see where derivative is 0, that you're guaranteed to have a local max or min there. So what I'm going to do is I'm going to give you an example of a function right now that has a derivative being 0 right there. What's the slope of the tangent line there? F prime is 0, right? The derivative is 0. Is that a local max or a local min? No, right? It just goes like that and goes up. So the theorem says if you have a local max or min and the derivative exists, the derivative must be 0. Does not say, I'm saying this like the second or third time now, it is not saying that just because your derivative is 0, you have to have a local max or min, right? Now there's something important in there I want to see if anyone in this class can get it. In the theorem, it says that if you have a local max or a local min, and the derivative exists, then the derivative must be 0. Why is that if the derivative exists part in there, in the theorem? You can still be continuous if your derivative doesn't exist. Can somebody here draw me, not up here on camera, but can someone just come pick up a marker and draw me an example of a local maximum where your derivative would not be 0? You do it? Try it. If you don't get it, then we'll just kick you out. It's no big deal. Just grab any marker.
Max? You want it to be max?
A local max.
This?
I can't see them more.
That's the max? It can't be...
I want there to be a maximum. I want you to draw me something that has a local maximum at a point. Like this has a local maximum here, right?
Yeah.
And the derivative is 0.
Yeah.
I want you to draw me something that has a local maximum, but the derivative is not 0.
Oh, that makes sense.
You want to rethink about it a little bit?
Yeah.
Okay?
Yeah.
Okay.
Can it...
You just go draw it. You either right or wrong. It's okay if you're wrong. You're going to be on camera for a few seconds. Go.
Does it have to be defined? Right?
It can't be a vertical line because, is that a vertical line? Oh wait, what did you do there? I think you're on the right track. What did you just do there?
Like if you make like a corner?
Yeah, do it. Do it bigger. Just draw your own. Just draw your own.
I don't know.
Draw the other side of it.
Like this one?
Okay, there, good, done. That's a local minimum, but yes, that's right. Okay, yeah, well, you didn't have that part. So let me put this on camera. Check this out. Look at this function. Is that function continuous? Did I draw it without picking up my pencil? Does it have a local maximum? What is the derivative there? Undefined, because it's a corner, right? Remember we had these corners where derivatives don't exist? Right? The theorem is telling us if we have a local maximum, here we have local maximums in both points, right? Both of these, and the derivative exists, then the derivative must be 0. Here you have a local maximum, but the derivative doesn't exist, so it doesn't have to be 0. Now you can do this for this same thing, like that. That would be local. I think that's what you were drawing. Okay? So here's an example of a local min where at that point the derivative doesn't exist. This will all start to become clear as we start using it. All right. We have a couple of more things to define, and then we'll try and get to the main idea of this whole thing. Something called a critical number. I'm going to draw you a function. I want us to talk about all the local maximums and minimums real quick. This right here would be a local max, right? What's the derivative there? 0. How about here? That's a local min. What's the derivative there? Does not exist. Derivative doesn't exist. Here, that's local max. Derivative is 0. Right around in here, it's hard to see it, but somewhere in here, the derivative is 0, isn't it? Because it looks like it goes and flattens out and then goes like that. Now, is that a local max or a min? No. So this is like the, what is that? The ugly duckling, the ugly stepchild. What is that? The oddball, right? This is the runt, whatever. It doesn't belong here. Has a derivative of 0, but it's not a local max or min, right? Okay. How about here? Derivative doesn't exist. But we have a local max, local minimum. This doesn't look like it flattens out. It kind of goes like that and then comes back up. So another local max, another local min. Derivatives here are 0, aren't they? Okay, so no matter how you draw a graph, doesn't it seem like if you're looking for maxes and mins, you should start looking where the derivative is 0 and where the derivative doesn't exist? That would be the most natural place to go look. Because wherever it's 0, we either have these humps or we got these flattening out things, right? And then anywhere it doesn't exist, we have something interesting happening also. So it would be very critical for us to be able to figure out where these things are happening, right? So critical, in fact, that we are going to call these places where these things happen the critical numbers of the function. The critical number of the function is a number in the domain where the derivative is 0 or the derivative doesn't exist. Those are what we're going to call the critical numbers. So if we imagine there being an x-axis down here, wherever this happens, C is called a critical number. Wherever that happens, well, I can't call it C again, I'll call it C sub 2, I'll call it C sub 1. This one would be C sub 3, this one would be C sub 4, so on and so forth, right? All of these things are called critical numbers of the function. So that's a definition.
It's interesting how the runt of all of those is the most exclusive.
The runt is the most, oh. I get it, C4, I get it. It's a level of humor bordering on sick. It's my dad's type of sense of humor. I didn't say they're bad, I just said it's kind of a... All right, here's Fermat's theorem. Again, we're going to just kind of look at it in a different form. If f has a local max or min at the point C, then C is a critical number. So if you have a local max, then it's either going to be the derivative is 0 or undefined, or does not exist. All right, we are finally to the main idea here. I don't think we're going to be able to do an example. So why don't we just call it right here? This is where we'll pick up, okay? We are going there. When it comes to this class, all right, moving ahead, we are going to be dealing with two different scenarios from here on out. We're going to either be talking about functions that are on closed intervals like this, or we're going to be talking about functions where the intervals are non-closed. So the function goes off forever in both directions, or maybe just in one direction. So it's either going to be closed interval or non-closed interval. We are going to have to look at each of these and be able to tell, you're going to have to tell me what the highest and lowest values of this function are. And here you're going to have to be able to tell me all of the local maximums and minimums of this function. The way you do it for each one is different. And what we will start next week is how do we do it for this. After we get through that, we'll go through how do we do it for this. All right? Have a good weekend. Quiz Tuesday, is that what y'all want? Yes? I wouldn't get into this. This would be a good time to finish up the L'Hôpital's, go back and review chapter 3, kind of brush up on everything, and that way you're clear to go into chapter 4. I don't think we'll have a quiz on Tuesday. I don't have enough material for a quiz.